Right, so welcome to the 8th lecture of the course Mathematics for Machine Learning. Um, Yesterday, after having briefly gone through Python, right, we started our journey into the mathematics part, yeah, and there we said that broadly speaking, machine learning is built on three or based on three branches of mathematics, which are linear algebra, probability, and optimization, right? And our first stop is linear algebra, and for that we had started discussing some basic things, right? So I started with this one, talking about the poetry of mathematics, which is like our general poetry. As I said, very quick review of that was that just like we have created worlds and spaces, objects, they have their rules of engagement. Mathematics also does that. And you know them as sets, numbers, functions, matrices, those kind of things. Yes, spaces, rings, fields, yeah. So of course, if you don't know all of them at the moment, it's fine. We will not use all of them in the course, but you have some idea of, for example, groups and spaces. So we saw last time, we started seeing some objects in the world of mathematics, like expressions, where you have variables, you have operators, you have constants. And we saw beyond single variables, you had the option to collect more variables, yeah. And one of those ways was, this is more relevant to us, otherwise you can of course collect multiple variables in sets, right, in groups. So it's for us this is more relevant here in vectors, matrices, and in tensors, and tensors can go on. This is three-dimensional or three-way tensor, four-way tensor, and so on. The machine learning related library in the major machine learning library in Python is called TensorFlow. Okay, so they have this, I think, connected to this tensor. And we also saw, okay, basically up to here we are dealing with matrix algebra, whereas after two dimensions we need to go into tensors, yeah. Right, this we saw last time. We were probably somewhere here defining a set, yeah. So a set was a collection of distinct elements which are well defined in some way, yeah. So they can be abstract or concrete. Here it was, we saw this one, yeah, I now recall we did this also, right? Subset, you know all those symbols very well. If you don't, you have the slide set, just read online, find a book, Google it, you will find these if you don't know any of these symbols, but you should know, they are from basics. So we have operations on the sets, we know sets, I showed you last time, the order of the elements doesn't matter, yeah, it's the elements that define the set, and they alone decide what a set is. And we had looked at some sets that we are very much familiar with in mathematics, numbers of different forms, yeah. So we have the real numbers, in that real, algebraic, rational, integer, natural. We had done this last time also, irrational, transcendental, all those kinds of numbers. Define this, yes, quick review. So we had seen square root of 2 is irrational, but it's not transcendental. And then there are irrationals which are transcendentals, yeah. So we had looked at this, that although it looks like the real number set is the biggest number set, but it's not, yeah, it's just part of a bigger story, which is the complex plane. So there then you add basically whatever you saw in the real case, now you generalize that, yeah. And we discussed the difference between imaginary and complex, right? So complex has real and imaginary parts, it's the most general case, yeah. And if its imaginary part is 0, it's real. If its real part is 0, it's imaginary, yeah. So we know that. We had stopped here, so let's slow down over here. there are predefined interactions in that world, right? Like in poetry I said शेख और वो जो आशिक होता है उनका वो उसको हमेशा मशवरा देता है कोई, yes, wise. So like that you have predefined interactions. Most familiar ones are, yes, these guys. But in general, what do we mean by operator? Let's say you have a set or a space or something, an entity, yeah, X, and you want to take some values from them, we'll call them maybe the input, and you want to operate on them, yes. You could take one value, yeah, no value, three values, you will see that, yeah. But most commonly we take, for example, two values. Say addition में आप क्या करते हैं? You take two values, yeah. So, but you're not limited to that. It's just a schematic to give the idea. Then you want to operate on them and create something new out of that, right? Which will be mapped into another set, yeah, which may very well be X itself, but in the more general case, doesn't have to be, yeah. So then x1 plus x2 equals y. You took two of the members from this place and transformed them, morphed them, whatever you want to call it, into a member of y, yeah. Now how we write that mathematically? Here it is, the operator plus is defined on what? X times x. This is not a product, this is a Cartesian product thing. Basically we are saying that the two numbers x1, the small x1 and x2 are taken from this set X and then they are mapped to y, yeah, in for this schematic, yeah. So you can have a general case, you can call it some sort of a W, a mapping, general mapping, which takes input from n which different sets or spaces which don't have to be the same, इसलिए हमने उनको अलग-अलग नाम दे दिया, right? So you will have multiple circles here, yeah, instead of just one you will have more here, x1, x2 and so on, yeah. So in the general case you can take many of them and then map them onto y, yeah. Plus is the easy case that we are familiar with, so just to get started there. Now the operators may have some properties of interest or of general use, yeah. कोई property आपके ज़हन में आती है? For example, we know that x1 plus x2 and x2 plus x1 lead to the same point in y, right? So ये कौन सी property? Commutative, yeah. So the operators have some properties that are of interest. Commutative, yes. What is not commutative? For example, subtraction is not commutative, yeah. So some other properties that we are often interested in, you're familiar with them, right? So I'm just going through defining these things. Associative, distributive, associative, commutative, yeah. They work on one operator, yes. But to define distributive, normally you need two operators. उसके ऊपर ही distribute होना होता है, right? So that's why, for example, here the distributive is defined on addition and multiplication, yeah. But you could define on omega 1 and omega 2, कोई भी operators हो सकते, right? So you have that. Now not only operators may have interesting properties, operators along with their sets, if you look at them together, there might be properties of interest and of analytical use. So for example, ये क्या show कर रहा है? कौन सी property show कर रहा है ये figure? एक बनाया ना, let's say I explain this, let's say that whatever I take from X, the input, the output also lands within X. Closure, right? Closure. So this is the property of closure. Now closure is not a property of plus or minus, right? Alone. Addition उनकी नहीं है. किस उसके साथ? It's a property of the operator and the set, right? So there might be sets which are not closed for the same operator. Yeah, we will see examples of that, of course. So consider set X and an operator on it. अब कोई जनरल ऑपरेटर हमने बना दिया, राइट, क्योंकि हम वो कंफ्यूज नहीं करना चाह रहे कि सिर्फ प्लस हो रहा है. या सो इट्स अ जनरल वे ऑफ राइटिंग एन ऑपरेटर. क्लोजर फॉर ऑल u and v taken from x, yes, their mapping or their function relation, the output also lands in x. ये तो मैंने एक दिखाया ना, but this requires for all. अगर कोई एक में भी ना हो, किसी एक जगह भी ये fail हो जाए तो closure नहीं है. Yeah, so this is a property of the operator and a set taken together. For example, we'll come to some examples, but can you read this property and tell me what's this describing? Identity, right? So we are saying, okay, does there exist an element within x, yeah, such that x operated on E or E operated on x? This may look strange now, yeah, but you will see, of course, addition में इसकी समझ आती है, yeah, लेकिन subtraction में all of a sudden plus my order जो commutative नहीं होंगे, there will be problems there, right? So we have to check both sides. Identity requires that. Otherwise, it's a limited identity. We can call that left identity or right identity, right? But the general identity has to be both-sided, yeah, and unique. So yes, is there an identity element? क्या करता है ये? It's basically saying that the operation of, and again, it has to be there for all of them, yeah, and which one is this? Inverse. Yes. So there exists for every x, for every choice of x, there exists an element in y within x also, because I am starting with closed operations and sets. The operation leads to the identity element, right? So then we call it the inverse element. Yeah. Okay. So these are some properties of analytical use and interest. And as I said, these properties are not just defined on a set or an operator. The two things have to be taken together. Yeah. So let's say z is a set of integers. है इसमें closure property? Exactly. So you cannot say yes or no. That's what I want to check again. Yes. Alone this question is not enough. You have to ask me with respect to which operator. Yeah. And you will see some of them have it, some don't. Right? Agreed? Why is the last one failing? Yeah. So it's not covered by integers. Yes. So there is no closure. So z is not closed under division. Yeah. But it's closed under addition, subtraction, multiplication. Yeah. So identity element of z under plus. Now from here on we will just summarize like this. Yeah. This kind. So integer, set of integers under plus. क्या है इसका identity element? You know it. Yeah. बहुत basic है, 0. और ये मैं इसलिए build कर रहा हूँ कि eventually we will take it to vector spaces, right? वहाँ पे फिर हमने उनके define करने होंगे. तो अगर आप, if you are very much familiar and थोड़ा revised है, you have made connections in your mind about these things. So you know that, yeah. Inverse element of z under x multiplication, right? It does not. Yeah. So you don't have one, right? Okay. Now why are these properties of interest? But मतलब बचपन तो नहीं अब है, स्कूल से कॉलेज से पढ़ते आ रहे होते हैं ना, commutative है नहीं है, all that. Why are we interested?
We want to develop some type of group.
Okay. Why?
We can classify some sort of data.
Okay. Any other answer? मतलब इतने अरसे से हम ये एसोसिएटिव है नहीं है, पता नहीं हज़ारों आपसे सवाल कराते हैं, R प्लस को है नहीं है, कितने टेस्ट कराते हैं, क्यों करते हैं हम सारे? नहीं वो तो आप बता रहे हैं ना. This is more like a cyclic argument that these properties are useful because they help us classify based on these properties. समझ आ रही? इनका अपना क्या फ़ायदा है? क्यों हम चाहते हैं कम्यूटेटिविटी स्टडी करना, एसोसिएटिवनेस, आइडेंटिटी एलिमेंट की एग्जिस्टेंस, इन्वर्स एलिमेंट्स की एग्जिस्टेंस क्यों चाहते हैं हम? राइट? सो these are the kind of questions that one needs to ask to. बाकियों के लिए लाए हो कि नहीं लाए? यार सर्दी है बहुत यहाँ. अच्छा. So कोई है और वजह ज़हन में क्यों करते हैं? शौक है हमें, मैथ के प्रॉब्लम बनाने होते हैं हमने. या सो ऑफ कोर्स एज आई बीन सेइंग दे आर ऑफ एनालिटिकल यूज. ऐसा नहीं कि हमें शौक है कि यार ये एसोसिएटिव है नहीं है, बड़ी अच्छा लग रहा नहीं है. राइट? देयर आर यूजेस फॉर दैट. A lot of mathematics deals with finding solutions and solution sets and general proofs. यही होता है ना बहुत सारा मैथ. You want to find solutions, you want to find solution sets. Now closure, identity, inverse are helpful, as we can be sure that mappings will be reversed and solution does not require expanding the set. Yeah. Like if you're telling me that the inverse exists, if you're telling me there is closure, I know that okay, the results of these operations will always be defined within this set. I don't need to expand the set, right? I cannot have undefined results. Yeah. Then again, the existence of inverse means ज़्यादातर आप क्या कर रहे होते हैं? 4x equals 6, find x. यही कर रहे होते हैं ना, सॉल्व कर रहे होते हैं. अब मैं आपसे कहूँ 4x equals 6, find x, और आपको श्योरिटी ना हो कि x पता नहीं एग्जिस्ट करता भी है, सोल्यूशन एग्जिस्ट करता है. If you know that for real numbers product does have an inverse, for example real number, integers में तो हमने देखा था नहीं था उसका, right? But for now if I tell you 4x equals 6, find an integer x that solves this, आप फौरन कहेंगे सॉरी नहीं हो सकता. Yeah, because that this set does not have an inverse element under product, right? So but real numbers have it. Yeah, mostly. So now they also help us understand nature and limitations of sets. Yeah, so they can help us expand our horizons of mathematics. और ये होता है, कोई नई चीज़ नहीं है. Square root of a real number, always a real number? नहीं होता ना. ठीक है, एग्जिस्ट नहीं करता. पूरा एक नया आपको फील्ड बनाना पड़ गया उसके लिए. क्या था? कॉम्प्लेक्स नंबर्स. Yes, fundamental theorem of algebra doesn't hold without complex numbers. क्या है fundamental theorem of algebra? Nth order polynomial has exactly n roots. Yes, अब अगर complex roots, complex set ही exist ना करता हो तो फिर कितने उतने रियल हैं, कितने बाकियों को आप कहेंगे हाँ कभी 3 एग्जिस्ट करते हैं, कभी 2 एग्जिस्ट करते हैं, बाकियों का हमें पता ही नहीं क्योंकि हमने वो सेट ही नहीं बनाया अभी. राइट? सो these properties also lead us to expand our solution sets, define new kind of solution sets. Yeah, so it's not just curiosity. Of course, real numbers are not closed under square root, so you have to, if somebody had to solve this equation, find real number x such that x square plus 1 is 0, उसके कभी sorry undefined, right? नहीं हो सकता. So that of course this leads us to, for example, coming up with a bigger set. Yeah, so because there is no closure, then the value might be going into some other set, and what's that set? और इसमें क्यों नहीं है वो, और उसकी क्या properties होनी चाहिए? So that leads us to new kind of mathematics and new kinds of solutions. आप पता है complex numbers के बगैर modern engineering would come crumbling down. Yeah, जितना हम analysis कर रहे हैं ना सारा कुछ उसके ऊपर चलता है. Yeah, so now that was about identity and those closure. Then these properties, commutative, associative, distributive, they are of course useful in simplifying expressions, right? Coming up with removing redundancies in our formulations. आप करते आए ना metric से वो simplify this equation, कर आगे वो छोटी सी रह जाती है. या क्यों possible होता है? अब this is a very useful expression, बहुत से fields में use होती है. Right, a plus b into a, हम naturally बोलते हैं हाँ ऐसे ही है. Yeah, but if we hadn't proven those, let's say, properties, or hadn't surety that those properties exist, or in problems where these properties don't exist, ऐसे operators जिन पे ये apply नहीं होती, वहाँ ये relation won't hold. फिर उसके लिए क्या करेंगे, होता है कोई नई बनानी पड़े आपको. Yeah, so imagine proving this thing and look at, if you carefully look at it, ये सारे आप use करेंगे इसके अंदर, लेकिन आपको feel नहीं होता. ठीक है, because you say okay ये तो ऐसे ही होता है. Yeah, so there are reasons for that. Now a very common type of operator is the binary operator. Yeah, वही जो plus minus या जो which takes two members from one and operates on them and creates one member. And by definition doesn't have to be like that, but the way the binary operation is defined, it is supposed to be closed. Okay, so it's a operator that takes two elements from a set, right, and its output or result is also within that set. Yeah, and that is a binary operator. You are familiar with many different kinds of binary operators. The definition implies that X is closed under F. So homework for you, this is binary. Yeah, so then there are nullary, unary, ternary, n-ary. It's called the arity of the operator. Yeah, पता है क्या होते हैं किसी को? नहीं, चलो इसीलिए homework. You have the hint here, by the way. Binary, ternary, unary. Yeah, unary operator takes one element. इसलिए दो ले रहा है ना, it will take one. कोई बता सकते हैं आप unary operator?
True with false होगा, एक का हम जवाब दे सकते हैं,
Complement ले सकते हैं, right? Complement would be 1 minus multiply by negating. Take x, make minus x. You don't need two operators, right? फिर nullary क्या होगा, कुछ भी नहीं लेता, फिर भी output दे. Yeah, so you have to see that. That's homework. But the most common operators are binary operators. Yeah, that we.
negation binary operation नहीं है.
How is it binary? So how do you define binary now?
वो ऑपरेटर जिसमें आपके पास ऑपरेंड दो,
हाँ.
तो negation में आप माइनस को तो किसी चीज से मल्टीप्लाई करना कोई सेंस नहीं बनता ना. negation actually means multiplying it by -1.
Multiplying by -1. What if I say, I'm just saying I am taking a mapping, you give me a real number, right, and I will give you its negative, opposite. Yeah, fx equals minus x. So I'm taking, how many operators am I taking? अब वो let's say आप assume कर रहे हैं कि 1 हर दफ़ा उसके साथ आ रहा है, ऐसे ही है. Am I asking you for 1? Fix तो कुछ हो सकता है ना उसके अंदर, right? So I'm not asking you to provide me two of them that I will multiply together, right? ठीक है, अगर मैंने -1 decide किया हुआ है तो वो तो fix हुआ हुआ है. I just need one, fx equals minus x. I am asking you only for one value. ऐसे ही है ना? या समझ आ रही? So उस पर देख लें. But that's the homework. Just look into these nullary and you will see examples of all of these. Right, so some examples. On the set of real numbers, this guy, FAB equals A plus B. It's a binary operation, right? A plus B. Is it a binary operation? What's required for it to be a binary operation? अब define करें ना, FAB equals A plus B, right? So what is, what's the second, what's the first condition? It should take two operands or values. Yeah, दूसरी condition क्या है? नहीं, वो तो हो गया ना, ऑपरेटर तो है. दूसरी कंडीशन क्या है? क्लोजर. बाइनरी ऑपरेशन इंक्लूड्स क्लोजर इन इट्स डेफिनेशन. क्लोजर है इधर. सम ऑफ टू रियल्स इज ऑलवेज रियल, है ना? क्लोजर भी है, तो इट इज. नाउ लेट्स से वी हैव अ सेट of 2 by 2 matrices, yeah, with real entries, and look at their product, FAB equals AB. We define the matrix product, right? So is that a binary operation? It is, right? So because 2 by 2 matrices with real values का अगर जब भी आप product लेंगे तो वो 2 by 2 matrix आएगा, and that's what you defined M. M is the set of all 2 by 2 matrices with real entries, right? Now take any two values from there, meaning take any two 2 by 2 matrices from that set, multiply them using matrix multiplication. The result is again 2 by 2, और अचानक उसकी values complex तो नहीं हो जाएंगी, right? So it is definitely a binary operation. Division on real numbers. Binary है या नहीं है? Except 0. Yeah. So it is a binary operation on set except for 0 where it is undefined. So yes, it is not really a binary operation, but usually we say these are called, we will see that later, these kind of operations are called partial operations, yeah, where there is one unique guy only, बाकी सारे पे apply होता है, ठीक है? So yes, in the strict sense, no, because for b equal to 0 it is undefined. Right. So multiverse का पता है क्या होती है? मैथ्स में नहीं वैसे नहीं, वो तो है, यूनिवर्स होती है ना एक, तो मल्टीवर्स क्या होता है? Parallel universes. Yeah, so there is the theory that the universe we live in is one of many universes, right? Not just galaxy वगैरह की बात नहीं हो रही, ये पूरी universe जो है, this is only 3 dimensions. Imagine there is a 4th dimension, then there can be full इसकी copies वहाँ हो सकती हैं, इससे मिलती जुलती हो सकती हैं, right? So the idea of multiverse in physics is very well known, but इसमें एक बड़ी मज़े की चीज़ होती है multiverse में, वो क्या है? It's not just the other universes are copy of our universe, right? Each one can have its own physical laws. Their gravitational constants can be different, right? All the other constants, their laws of physics can be different. Each of them can have a different set of laws. But of course, it's theoretical, yeah. But we are getting close with string theory to find new dimensions. But anyway, I like this idea because this is what math also does. What math does is it also likes to create its universes. Each universe has its objects and then it has its own laws. Okay? Now you want the laws and the objects to be meaningful. ऐसे laws नहीं डालें जिससे आपको कोई analytical फायदा नहीं है. Yeah? So what math does, it creates its universes in the form of structures, mathematical structures. कोई structures पता है आपको math में? कोई different आपने सुने होंगे? Metric structures, topologies, measures, graphs, algebraic structures. Yeah. So what is a structure for our purposes? It's a set of objects with some features or laws. There's a multiverse में every universe has its own objects, stars and planets and whatever, and then it has its own laws. एक में हम रहते हैं, उसमें ये laws हैं, ठीक है? एक और हो सकती है जहाँ antimatter dominant हो और matter गायब हो गया हो, right? So you could have different kinds of laws in there. So in mathematics, we have different kinds of structures which are basically sets of objects with their features and laws. Yeah. We are mainly interested in this guy with the arrow, algebraic structure. Okay. So what is an algebraic structure? So now undergrad के math में क्या होता है? Algebraic structure. याद नहीं इस बार है? Right. So a non-empty set, yes, this is where the story starts. Yeah, a non-empty set with a selection of operations on the set and a finite set of axioms that the operations must follow. Objects हैं कुछ set है, उसके अंदर कुछ objects हैं, elements हैं, right? Non-empty है. Then you have operators that operate on those sets. जैसे अभी हमने प्लस माइनस देखे, इस तरह और भी बना सकते हैं आप. They operate on those sets, and then there are laws that the operations must follow. या उनको हम axioms कहेंगे. Axiom क्या होता है मैथ में? हाँ वो तो रूल तो जनरल हो. आप गाने प्रूव नहीं कर सकते, right? So axioms are statements you cannot prove, and math is built on axioms, right? So how logical is math? देखिए ना, आप पूछते जाए ये क्यों ये क्यों ये क्यों, एंड में मैथ कहेगा इसलिए कि बस ये एग्जियम्स हैं और हमें नहीं पता, तंग नहीं करो. तो ये तो और भी लोग करते हैं, राइट? सो प्योर लॉजिक डजंट हैव एनी मीनिंग बेसिकली, या बिकॉज ऑल थिंग्स आर बेस्ड ऑन एक्सियम्स. सो अगर हर चीज़ एक्सियम पे बेस्ड है जितनी हमें समझ आती है, और एक्सियम को हम कहते हैं कि भी सॉरी मैंने प्रूव नहीं करना है, ना ही मैं कर सकता हूँ, फिर क्या लॉजिकल है क्या नहीं है मुश्किल है बताना. या सो anyway, this is an algebraic structure, and I like to draw it like this. There is a set, 3 parts हैं इसमें. There is a set. अब वो अकेले सेट का मुझे फ़ायदा नहीं है, नंबर्स पड़े हुए हैं, ऑपरेटर्स आपने डिफाइन नहीं किए हुए, कोई फ़ायदा है? ज़्यादा से ज़्यादा गिनती कर लेंगे मेरे पास कितने सेब हैं तुम्हारे पास, इससे ज़्यादा तो कुछ नहीं हो सकता, राइट? यू नीडेड ऑपरेटर्स फ्रॉम द स्टार्ट कि मैं जमा कर लूँ अगर सारे तो कितने पैसे हो जाएंगे या कितने सेब हो जाएंगे, कितने ऊँट हो जाएंगे मेरे पास. सो यू नीड ऑपरेटर्स ऑन दोज वैल्यूज़ इन द सेट, right? And then you need some sort of axioms or rules that they should follow, which will make the analysis meaningful and easier. Now इसमें interesting बात ये कि जो third part है ना, ये कोई शर्त नहीं है. It's not like a set has to be associative with with an operator. It's not that it has to have identity. It has to have नहीं है, ठीक है. कोई we cannot prove कि ये हमने क्यों डाले हुए हैं, किसी पे हम कुछ निकाल देते हैं. Yeah. So what happens if I change the set, or I change the operators, or I change some of the axioms? I get a new universe, right? उस universe के अपने objects हैं, उनके अपने rules हैं, right? उनके अपनी interactions हैं. So you can create basically as many universes as you want with their rules and with their objects. This is the multiverse of mathematics. Yeah. So each choice leads to, you could have the same set but replace this by another operator. It's a new universe now. Yeah. Or keep both of these same and take away one of these. Because ये कोई लाजमी तो नहीं है, आप सेट करें. You are creating this. Why we create these things? Because जब हमारे सामने we get certain sets of problems and we realize to solve them, we need to create a certain set of operations and rules that will help us analyze this problem. That leads us to create new structures. Yeah. So this is the structure group, yeah, which we are then further interested in. There are more structures, we will come to that. तो अभी हम कहाँ से शुरू हुए थे? From mathematical objects. Yeah. Within that there are mathematical structures. In the structure we saw algebraic structures, which were more precise than mathematical structure. Mathematical structure क्या था? ज़्यादा broad definition थी. ये a set of object with some features and laws, बस ज़्यादा generic है. Yeah. Within that there are algebraic structures which say, okay, now a bit more specific here. There is a set, there are operators, and there are axioms, that the rules or laws that we have enforced on it, yeah, or we want them to follow, and then they create this. Within algebraic structure there is a group, जो आप लोग mention कर रहे थे. So what is a group? Right. So I like to call it, as you say, I like to call a group is a set with a set. Fine. So it's a set of objects with a set of rules. Yeah. And अब मज़े का math right? So you know this thing probably from undergrads. If I teach this course at undergrad level, of course I'll keep it a bit simpler or not go, but I know many of you have done these things much more advanced than this. Yeah. So I want to show you these things in new light and I'll connect them to our own work also in machine learning. So let's say you have a set G and an operation. याद आए वो notation, we have seen that. Yeah. Now ये operation binary है या नहीं? Binary है, दो ही conditions थी, it takes two and closure भी है. So by looking at that you can say it's binary, right? It's a binary operator. Now define on G, then this is a set, right? And here is the operator, binary operator. They don't make alone, they don't make a group. Group कब बनता है? When you take them together like this and for some axioms on them, right? Again ये कोई उनकी property या कोई वो नहीं है कि universal कोई चीज़ है. These are rules that if they follow, the results will make more sense to us, and the analysis would be more meaningful. So firstly, we want closure. We want G, this G, the set G, to be closed under this binary operator. Yeah. So since the way we have already written it, it is closed. That's fine. Associativity. We want it to be have association. बता दियो आपको याद है association जैसे product में होती है, addition में होती है, right? Like that. It should have a neutral element and it should have an inverse element. I'm not going to spend time here because we have already seen these properties in the more general sense of operators. But now with this we are defining an algebraic structure. Yeah. So क्या बना फिर एक group क्या है? What is a group by this definition? Yes. नहीं, बीच में एक चीज़ मिस होगी. With an, हाँ, ये तीन चीज़ें हैं, इसके बगैर नहीं ये चीज़ें. Algebraic structure में तीनों चाहिए होते, right? A non-empty set, some defined operators, binary operators mainly, and then axioms on their interaction. Yeah, and that is, and कौन से axiom है? ये चार. Okay. Now अगर हम एक और इसमें डाल दें, one is missing by the way. कौन सा है इतना मशहूर? Commutative is missing. So group doesn't require, yeah, commutativeness. But अगर हो तो क्या कहते हैं इसको? Abelian group, right? So fine. Again, nothing magical about a group being abelian. बस उस पर वो enforce करने से कुछ और आपको analytical फायदे हो जाते हैं. Sometimes this is too restrictive, so you don't want to put it there. Okay. Matrix products are not commutative. So क्या करें, बस abelian नहीं है, छोड़ दें काम करना. Right? So we realize okay, matrix products में काम करना headache होता है. क्यों होता है? सिर्फ इस एक property की फ़र्क से तकरीबन commutative नहीं होती. Right? So it becomes very challenging to do those things. As an example, a simple inverse is 4x equals 6 है तो invert कर दें. पर a b equals y, अगर a and b are matrices तो इन्वर्स निकालना या a x equals y, a का इन्वर्स निकालना एक पूरा फील्ड है, राइट? और फिर भी सही नहीं निकलता. कोई ना कोई वो इल कंडीशनिंग हो जाती है. सो एक वो प्रॉपर्टी ड्रॉप हुई, लेकिन द प्रॉब्लम इज दैट टू मेक यूज ऑफ matrices the way we want to, we have to give up commutativeness. Fine. ठीक है. So there are requirements. Yes, if you add, so basically a set with a binary operator and 4 axioms enforced on it. Fifth भी डाल दें जो कि commutative है तो abelian group हो जाएगा. और डालते जाएं तो क्या बनते जाते हैं? Rings, field नहीं, और axioms डालते जाएं. मुख्तलिफ groups बनेंगे. If you change this set, you change this operator, ये तो लाजमी है group में. Yeah. If you change the set and the operators, you will get new groups, right? But if you add more axioms on top of that, so पहला एक डाला हमने पांचवा abelian, add more, you start going into rings, fields and those things. Yeah, वहाँ हमने नहीं जाना. ठीक है, क्योंकि हमारा काम इससे हो जाएगा. The general linear group, very much of interest to us. ये सारा linear algebra की तरफ बात जा रही है, right? So the general linear group, basically we say is this group. कहानी सेट से ही शुरू होती है हमेशा. या a set of n by n matrices that are also invertible. Okay. Of course, there are matrices that are not invertible. Like we want to have some set where we can analyze things. Yeah, and we assign an operator to it, the matrix multiplier, yeah, or the matrix multiplication, and with this is called a general linear group. Now it's up to you to prove that it follows all the axioms of a group. मैंने तो अभी सिर्फ set और operator बताया. Set क्या है? The set of all n by n matrices that are also invertible, meaning A inverse exists. इस condition को डाल के I have helped you because इसको डाले बगैर there is no general way to see that the number 4 will be satisfied, for example, right? But by adding this in the definition, I made sure that चौथी तो meet हो जाएगी, right? Commutative तो required थी नहीं पहले ही. So you can check, homework for you is to check that it satisfies all 4 axioms. एक तो मैंने बता दिया, चौथा तो by definition है. I defined the set in a way that I'm saying it's all n by n matrices. N by n समझ रहे हैं matrix, right? N rows, n columns, yeah, simple. That are also invertible. Since matrices are matrix must be non-commutative, the group is not abelian. Yeah, fine, we know that. So now within the algebraic structure we are interested is the vector space. Okay, so कहाँ से बात हुई? So before that mathematical structure, inside that algebraic structure. Algebraic structure में एक हमने बताया group. Yeah, now we are going to look at another algebraic structure. Group की वो requirement थी, क्या थी? Set, operator और वो 4 axioms. Yeah, वो group की थी. Structure की ज़्यादा broader requirement थी, some non-empty set, some operators and some axioms. कौन से हैं? कोई नहीं बताया. Yeah, so things are narrowing down. Yeah, now we are here on vector space. क्या होती है वेक्टर स्पेस? सुना है क्या होती है? Scalar multiplication वगैरह. That's the new stuff that will show up. Yeah. So I like to call it group को मैंने कहा था a set with a set, right? A set of objects with a set of rules. This is for me a set with a set and a set. ठीक है. So a vector space is a set of vectors. पहले तो ये अब set भी थोड़ा सा इसमें specify हो गया. It's a set of vectors, yeah, with a set of inner rules and a set of outer rules. Let's talk about that. This has nothing to do with inner product and outer product. वो और चीज़ होती है. These are inner rules. But there is a problem before going into vector space and coming out with something meaningful. We really need to look at some other topics. Yeah, थोड़ा सा basic से आएंगे क्योंकि if we go directly, maybe you miss some of the connections. So let's see that. Game of knowns and unknowns. ये आपको पता है. जब भी linear vector matrices की बात आती है, कहाँ से शुरू होती है कहानी? System of linear equations, right? So we need to first maybe revisit that a bit. Maybe in a new light, let's see. One unknown, one linear equation. Yeah. So which one of these is a linear equation? Left one. Yeah. So it has to be, if I had here cosine 30 x square equals 1 to 8, is it linear? Huh? तो linear equation की definition क्या होती है फिर? Right. So this is not. What about this one? If I make this, is this linear? Right. So the linearity is with respect to the unknown. Yeah. So the unknown has to be linear. या कोई उसकी power, कोई cube, कोई logarithm, कोई ऐसा आप allow नहीं कर सकते. Yeah. So a linear, a simple one known unknown, one linear equation. Yes, you can linear in the unknown, you can solve this. Yes, it has one unique solution. क्या है वो solution? So you do just one linear equation to solve for one unknown. Yeah, there it is. It represents a single point on a number. Okay, fine. One unknown and no equation. फिर क्या होगा? Let's say I ask you to find x, but I don't give you any equation. Then I have to give you something. वरना तो सारी universe हर value उसकी solution set है. Yeah. So let's say I don't have an equation, but I give you an inequation. Yeah. So one unknown but no equation, पर कोई और information है मेरे पास. Let's say 2x is less or equal to 16. Now here you had a unique solution. Yes. इधर क्या होगा? Firstly, it is underdetermined problem, right? Exact value निकालना नामुमकिन है. Infinite solutions you have, right? ये नहीं कि इसका solution exist नहीं करता. Infinite है, बहुत सारे हैं, we cannot choose from. So, okay, this whole line from below 8 is the solution, right? One unknown, two equations and a scam. Scam क्या होता है? फ्रॉड होता है, राइट? यहाँ क्या फ्रॉड हो रहा है? देखिए, दो you need two equations. Normally we tell children that you need two equations to solve for two unknowns, right? फिर उनको ये solve करने को दे दें. तो scam हो गया, right? हो जाएगा ये solve. Can you solve this for x? One equation, two equations and a scam. In this case, for two unknowns, we will see that later. Maybe I went ahead a bit, but for now, let's see this one. Looks like I have been given two equations, right? But there is a fraud in here. What is the fraud? The second equation carries no new information, independent of the first one. If I didn't know this, then it has information, right? Or if I didn't know this, then this one has information. But none of them has any information in the presence of the other one, any new information. नहीं है ना? So it looks like you have two equations, but in reality you have only one equation. So we can say in 1D case, one is a scaled version of the other. Yeah, there is no new information. Why? Because the simple rules of maths tell me that if 2x is 16, that definitely 4x had to be 32. There is no new information in there. So this is overdetermined system. Why? Because the number of equations is more than the number of unknowns. Yeah, but it is still consistent. What do we mean by that? Both of them give the same information. Scam hai because I didn't actually need the second bit, it was just a redundancy there. But anyway, okay, still one unique solution exists, right? दोनों क्योंकि consistent हैं, they are both giving the same solution. Fine. Now, a unique point on number line can only be represented by one distinct linear equation, right? Any other linear equation representing the same point would be a scaled version. You can घर जाके भी सोच लेना, इस पे simple है, एक point का आपने बनाना है. So is 4x equals 6. So if you want to represent the same point, then the whatever equation you make will have to be a simple scale version of that. दोनों साइडें same number से multiply होंगी तो आएगा, otherwise it's not possible, right? Okay, one unknown, two equations and a lie. अब ये different है. Where is the lie? Inconsistent हो गया. Previous system was overdetermined but consistent. So a solution still existed, a unique solution. Here they are overdetermined and inconsistent, right? So one of these is not telling the truth or something like that, yeah, because they are pointing to two different solutions. Which one should I pick? Yeah, so maybe we should give up both of them, or maybe we need to come up with some rules to make choices in such situations. This is very critical. A lot of machine learning is about that small thing there. Finding rules जहाँ inconsistencies आ रही हैं, variations आ रही हैं, उसके बीच में से कुछ निकालना है हमने. Yeah, we will see that. Now, as I said, this is the same thing, otherwise it represents a different point. Now, in real applications, this is the slightly surprising for some students maybe. We are not dealing with मैथ में तो हम आपको यही कराते हैं ना कागज़ पे कि हमेशा डिटर्मिन्ड, वेल डिटर्मिन्ड और कंसिस्टेंट सिस्टम. Real applications almost always deal with over-determined inconsistent equations. Okay? Why? Because of this guy. Randomness. Yeah? There are noise, there are many errors, there are variations. ये चीज़ आपको खुद ही समझ आना शुरू हो जाएगी आहिस्ता आहिस्ता. Because let's say, what do we mean by variations? As I've been mentioning, there is no one universal picture of a car, right? So from one picture to another, the car varies. Yeah. So there are natural variations. Yeah. You will have to give your machine learning algorithm a lot of data. Yeah. Over determined भेजेंगे उसको आप और उसमें inconsistencies होंगी. उसमें ढूंढना ये है कि ये इनकन्सिस्टेंसीज के बावजूद क्या इसमें पॉइंट कौन सी जगह हैं जो ट्रक से डिफरेंट होती हैं फॉर एग्जाम्पल, राइट. सो ओवर डिटर्मिन्ड एंड इनकन्सिस्टेंट सिस्टम, लेट्स से वी हैव दिस. ये ओवर डिटर्मिन्ड है. क्यों है ओवर डिटर्मिन्ड ये? Because there is one unknown and 3 equations. Yeah, but this is the kind of problems we normally solve or work with in machine learning. Yeah. And yeah, we see that there is no solution, but can we devise a strategy to pick a point these are most likely referring to? Yeah, तो इनसे क्या आपको फीलिंग आती है? 3 different points बता रही हैं ये. Yeah, but 2 of them are pointing to almost 8, right? कोई एवरेजिंग अगर हम करेंगे जब फिर अब यहाँ तक बात आ गई कि वी हैव इनकन्सिस्टेंट सिस्टम एंड इट इज़ ओवर डिटर्मिन्ड. these are the points they are showing us. Can we, yes, no solution, but can we devise a strategy? Okay, let's see. Let's say the 3 points are S1, S2, S3. Okay, the equations are representing them. Perhaps we can take their mean. Okay, say okay, हमें पता है वेरिएशंस आएंगी लेकिन 15 इक्वेशंस हैं उनका रिजल्ट 8 के करीब करीब है और 3 इक्वेशंस हैं उनका रिजल्ट 4 के करीब है. तो हमारा जब एवरेज लेंगे तो आप 8 के करीब फैसला करेंगे, राइट. सो in machine learning, in these fields, we don't just like mathematics, we don't say, oh, sorry, solution doesn't exist. Yeah, inconsistent, bas band kar diye, right? We actually know we will be dealing with inconsistent systems. Yeah, so or we could do something more elaborate, maybe arg min x minus s square plus. Yeah, notice this thing is talking about finding the least of something. Yeah, and this thing is, these are squares. ऐसे ही है, ये इकट्ठा इनको पढ़ें. This is gonna show up again and again. Least square solution बार बार आएगा ये, ठीक है. I just wanted to show you from the single point क्योंकि this is what builds up later. Yeah, lot of regression, classification, they are built on this guy or variants of it. पर आइडिया यही है. Yeah, so what does this represent? Yeah, I already gave you idea. It's basically the least squares, but we will come to that later. So the answer to this question, I said the systems we'll deal with are inconsistent because there are variations. Yeah, there are randomness. ठीक है, आपने रीडिंग ली है तो if you gave one voltage you should see current I, but you sometimes see I plus 0.001, sometimes you see 0.003 for the same V, or even your V might not be exactly set up, right? ये एक और तरह की randomness है. The variations, as I told you, in different instances of the same thing, a car, your face, दिन में कैसा लग रहा है, रात में क्या, those are also variations. सारी randomness है. Yeah. So okay, we understand that there are inconsistent equations, but why would we want to deal with overdetermined? Any idea? सवाल समझ आ रहा है? More choice in selection, right? Average किसी ने बताया, right? देखिए जब आपको पता है कि इन सारों को ठीक नहीं पता, थोड़ा थोड़ा गलती है, तो और सारों से काफ़ी सारों से पूछ लें, right? Statistic averaging करना चाह रहे हैं आप, for example, right? So then it makes sense to use a lot of information so that the within that randomness you can find, okay, what are most of them pointing to, right? जो कि average का idea होता है, yeah, variances, covariances, correlations, उनसे हम उसको study करते हैं. So yes, we know there will be randomness in our data. Then we realize, okay, if there will be randomness, we are better off working with a lot of this data. Why? अब example ये वाली, same example, if I had said no, this is inconsistent, but imagine just working with this equation, आपका जवाब तो गया, right? क्योंकि you know there are randomnesses and you might have picked an outlier just to remain fully determined. हमने over determine नहीं करना, under determine नहीं करना, एक variable है ना, तो एक ही equation चाहिए, right? But as soon as you realize there is randomness, it's in your favor to go over determined. Okay, so yeah, just for curiosity, can we have one unknown, one equation and no solution? हमने सारे combination देख रहे तो मैंने कहा ये भी डाल, ठीक है? One unknown, one equation and no solution. So suppose I give you A and B, can you find X?
If A is equal to B, then there will exist no solution.
Sure.
A
A
is
equals
equal to
0. B तो फिर तो one answer हाँ, ठीक, 0. So there can be situations, yeah, where you have it, apparently you have an unknown and an equation, क्या मसला है, solve कर लें उसको, yeah, but it could happen that there is no solution. क्यों? Division by 0 है, yeah, but also because this equation doesn't give you any new information. We know that 0 time anything had to be 0. इस information, इस equation ने तो आपको कुछ भी नहीं दिया, right? So either it's lying or it's giving you an impossible equation. Now that I started with the points. Why? Because believe me, जो हमने बातें कर ली हैं ना, यही चलनी आगे. ठीक है? We started with single points. Yeah, single equation 4x equals 16, yeah, or 2x equals 16. One equation, one unknown, all good, solve हो गई. ठीक है? Then we saw one unknown, two equations, but they were consistent. So the system was overdetermined and still had a unique solution. Then we saw one unknown, two equations, and they were inconsistent. Yeah, so then the system had more than one solution. When we saw that it's in our favor to use that. So let's see now this one, from points to lines. Two unknowns and some linear equations. Yeah, what we have discussed is gonna generalize here. ये solve हो सकती हैं दोनों. Yeah, so you have two equations, two unknowns. It's not overdetermined. The system is not underdetermined, and there are no inconsistencies. अगर आप solve करके देखें, it's a very simple, straightforward process, and you know this is the intersection point. Yeah, they have one. Two unknowns, one equation. Underdetermined हो गया, right? So now infinite solutions like before, या जहाँ पे वो था one unknown and no equation, एक in equation दी हुई थी आपको. So you had infinite solution. Here you have two unknowns and one equation. So this whole line now is a candidate. और क्या कर सकते हैं, ठीक है? इसमें भी solution निकालने का एक तरीका है. Minimum norm maybe. We will see that. Yeah, you agree on convention. Say you agree on something. Yeah, so two unknowns, 3 equations and a scam. Now this system is overdetermined, right? Apparently है तो overdetermined ही. Scam क्या है इसमें? Again trickery है. Second equation adds no new information, right? It's just the repetition of the information in the first one. Yeah. तो इस केस में क्या होगा? Still one unique solution exists, right? क्योंकि ओवर डिटर्मिन होना बुरी बात नहीं है, ज़्यादा मसला इनकन्सिस्टेंट होने में, राइट? सो दिस इज स्टिल कंसिस्टेंट, so you can find a solution. But notice what's happening here is, why were we able to find a unique solution? Yeah, see, दो अननोन्स के लिए सॉल्व करने के लिए कितनी इक्वेशन चाहिए होती हैं? 2, अगर वो दोनों इंडिपेंडेंट हो, न्यू इन्फॉर्मेशन दे रही हूँ, ऐसे ही है ना, राइट? सो असल में तो हमें 2 चाहिए थी, तीसरी तो एक्स्ट्रा है, ठीक है? सो what if we can say that these 2 independent equations, the true worth of this system, इस सिस्टम की असली वर्थ कितनी इक्वेशंस है? 2 है, राइट? रैंक कह दें फॉर इंस्टेंस, लूजली स्पीकिंग, दिस विल कनेक्ट टू द कॉन्सेप्ट ऑफ रैंक इन अ मैट्रिक्स. या सो यस, फाइन, वो that lies exactly on the other one. ये दोनों एक ही इंफॉर्मेशन दे रही है मुझे, right? Exact same information, but still there is a unique intersection point. Now ये आप पढ़ सकते हैं and you can try to see if that makes sense. Unique point can only be intersection of 2 lines. Any third line passing through that point will necessarily fit one of these 2 things. क्या होगी? Either a simple scaled version of one of those, or a scaled and summed, मतलब linear combination of those 2. Linear combination में भी नई information नहीं होती, क्योंकि आपने बेसिक मैथ्स पहली 2 पे लगा के मुझे वही बात बता दी, तो पहली 2 से मुझे पता चल चुकी है, अब मज़ीद क्या बताना है आपने, राइट? सो अगेन a lot of things showing up that we will come back to in developing our machine learning algorithms, right? Linear combinations, scaling and summing, scaled versions. Just a quick recap, mathematically कैसे define करते हैं linear combination को? Let's say you have been given some objects, could be vectors, could be variables, could be E1, E2, E, yeah? So a linear combination, every combination of this form where alpha are scalars, yeah? क्या करना है आपने? उनको लेना है और उनके साथ एक एक वेट लगा देना. This should already remind you of the neural network kind of, neuron kind of thing, right? Inputs आ रहे हैं, उनके ऊपर वेटिंग और ये linear combination बन रहे हैं. So I like to call it scaled and summed, because you take each, you scale it by some alpha, and then you add it to the scaled version of the other one, and so on. Yeah, and of course these alphas, most of them could be 0 also, right? So you could get jitne, each selection of alphas will lead to a new linear combination. Okay, so इसको हम सुपरपोजिशन भी कहते हैं, या लीनियर कॉम्बिनेशन. नाउ कोई लीनियर कॉम्बिनेशन आपको याद आते हैं जो आपने देखे हो मैथ में पहले, राइट? सो तो वही न्यूरल नेटवर्क का हो गया, फोरियर ट्रांसफॉर्म हो गया, फोरियर सीरीज वगैरह जो करता है, या सो यू नो मैनी ऑफ देम, and you can try to recall others, that's fine. So let's get back to this one, 2 unknowns, 3 equations and a redundancy. So in this case what's happening again is that I have been given 3 equations, but one of them is redundant. Yeah, previous case mein one was a simple scaled version of the other. In this case the third one is made up as a linear combination of the first 2. Yeah, so ये इतना obvious नहीं है, पिछला तो बहुत obvious था ना ये case. This case was very obvious, yeah, but because this was a simply scaled version, yeah. Here it's not obvious, and but if you look at it, it's overdetermined, it's consistent, but it's kind of its rank or the true worth of this system is 2 equations, not 3, yeah. So still one unique solution, okay, because two independent equations are all you need to solve uniquely for a system, yeah, for 2 unknowns. As I said already, again you can read the same statement that only 2 lines can pass through one point. A third one passing through them will either be a scaled version of one of them, or it will be a linear combination of the other 2, yeah. So but since they are still consistent, we can find the solution, fine. 2 unknowns, 2 equations and a lie. Now you have 2 unknowns, 2 equations, solution फिर भी नहीं निकल रहा कोई भी, ये नहीं कि infinite निकल रहे हैं, है ही नहीं इधर, yeah, because now you are getting them parallel to each other, yeah. In fact 2D में it will always be like that you will have these kind of parallel lines. This is your homework. Convince yourselves that 2 mutually inconsistent linear equations in 2 variables will always lead to 2 parallel lines. ठीक है, सोच लेना इस पे थोड़ा समझ आ ठीक. So another way of lying here, overdetermined and inconsistent. Again now we are back to the inconsistent problem. There is an extra equation, but they don't match. पिछले में at least extra थी, match तो करती थी, yeah. But again, this is the kind of system we will mostly be working with in machine learning, yeah. So no intersection point, कोई उसमें हर 2 जो हैं वो अलग point बता रही हैं, ठीक है. So no solution. This is where kind of pure math will stop, right? You say, okay, no solution, bye bye, right? But this is not where application should stop, yeah. So कोई है तरीका, फिर कोई तरीका जैसे हमने उधर किया था लाइन पे, इधर भी कुछ कर सकते हैं. Maybe we can agree on something. Maybe we can say, okay, let's agree on some way of finding perhaps a compromise solution that does equal justice or injustice to सारे बराबर ना खुश हो जाए सारे पॉइंट, या ये फिर ऐसा कोई निकाल लेते हैं. Maybe choose a point that is smallest squared Euclidean distance from the 3 points, yeah. हाँ, so Euclidean distance याद है between 2 points, yes, and the square of this would get rid of the square root, थोड़ा analytically easy हो जाएगा, वरना कोई मसला नहीं है इतना, yeah. So let's say the 3 points have coordinates here. Maybe we can find the minimizer of their squared Euclidean distance, total Euclidean distance का square, again least squares, yeah. तो ये बीच में एक point नज़र आ रहा है आपको. So as I said, in real data applications we worked with overdetermined inconsistent systems, and techniques like these of deciding between those help, yeah. From lines to planes I won't go in that detail, you already know now. समझ आ गई, हमने point से शुरू किया है या फिर line पे आए हैं. Now in plane same situation will carry on. Idea वही है, ठीक है. Fully determined and consistent, fine. Overdetermined but consistent, उसका एक. Overdetermined and inconsistent, most जो simple math में most simple case के पास कोई solution नहीं है, but most interesting for us, right? And then how do we resolve that? If there is inconsistency, we want to still find a solution that kind of fits nicely in there. So from linear equations to matrices, yeah. Take the time. I'll just start this one briefly, but we will start from here again, yeah. पर थोड़ा सा आपको वो मैं दे देता हूँ इसका. We want to go from here to matrices. Smart way of handling linear equations basically. So you know this one. You have a system of linear equations, let's say, and aij are real, for example. They don't have to be, but हमारी problems में अक्सर होते हैं, इसलिए it helps us to define like that. Can I write it like this? लिख सकते हैं? Yeah, easy to see that you can write that. X here are assumed to be the unknowns, yes, and A's and B's are known. But then this can be written like that. Ax equals B, yeah, that is your matrix representation, yeah, that we work with. Here you have some, mostly क्या होता है, यहाँ knowns होते हैं, यहाँ पे unknowns होते हैं, और ये, but in machine learning उल्टा होता है, right? Usually these represent the weights, especially in supervised learning. These are the weights, you don't know them, and these are the inputs that you do know, आपने दिए होते हैं वो value, yeah. And अगर supervised learning है तो you know these for training, अगर नहीं unsupervised है तो you don't know these either, yeah. So we will define the set of real matrices, m by n real matrices as this. So ये notation काफ़ी use होगी, इसलिए you should be comfortable with it. It's the set of m by n matrices with real values, yeah. So what does this remind you of? This तो नीचे हमने notation उसकी बनाई थी, आज हमने देखी एक चीज़, linear combinations, right? It's saying that B is a linear combination of the columns of matrix A, right? So we are trying to find the weights x1, x2, x3 of that combination, right? So these are the weights we might be interested in. So we see these again next time, inshallah. We'll stop here and I can take your questions.